Hello everyone. Today we are going to discuss section 15.6 on triple integrals. Remember, we are done with double integrals over rectangles, double integrals over general region, double integrals using polar coordinates, double integrals, no, not double integrals, surface area, and now we are working on triple integrals. Now, of course, triple integral. Just a little introduction. What happens is, let me get this right first. Okay, a triple integral, right? Yeah, triple integral. Okay, so triple integral would be something like three integrals dv. In other words, you can write this as integral dx, dy, dz. So let's say this is from x1 to x2, this is y1 to y2, this is z1 to z2. Okay, you can, using Fubini's theorem, the integrand is 1. Okay, now using Fubini's theorem, you can change the limits of integration and write this as however you want. Like for example, you want to write y first, you can write dx dz, so you can write y1 to y2, x1 to x2, z1 to z2. Or you can also change the limits of integration on z, so write dz dy dx, so that means this is z1 to z2. You have y1 to y2, then you have x1 to x2. You can also change your limits of integration and write like this. So when you evaluate triple integral, what you get is a volume. Okay, volume. Loosely speaking, if you allow me to speak like that, for example, this will give you the length. Okay, and this will give you the width. Okay, and this will give you the height. Okay, I hope I'm on the screen. If not, please excuse me. HEIGHT. So the volume is going to be the length times width times the height. That's going to be dx, dy, dv. So whenever you use triple integrals, you get the volume. Okay, but in some problems, volume, volume, right? Yeah, volume. In some problems, what you end up doing is your integrand is not 1 always. You would have an integral, let's say something like some function f of x, y, z, and let's say you have dx, dy, dz. Okay, and this entire domain D. So then what do you get? Do you still get the volume? That's the question that you have. But you don't get the volume. This is the volume, and this is going to be the density. So density times the volume is going to be the mass. So the triple integrals will give you the volume when the integrand is 1. If your integrand is not 1, triple integrals will give you the mass. That's the first thing that you have to understand. Okay, again I repeat, triple integrals will give you the volume if your integrand is 1. If your integrand is some function f of x, y, z, that is considered to be density times the volume. Using physics, in physics you get density is going to be density. Okay, in physics, density is represented by rho. Density is mass over volume, so mass is going to be density times the volume, and the density is given by the function f. So if your integrand is 1, triple integrals will give you the volume. If your integrand is a function f, then the triple integral will give you the mass. First thing. Then I want to compare and contrast it with double integral. Okay, double integral is, let's say you have f of x, y, and you have dx, dy over the entire domain D. So this is going to be your length. Okay, this is going to be your length, and dy is going to be your width. Okay, and your height is not coming from the limits, but instead your height is going to be from the function f. So double integral is nothing but the A volume is nothing but length times width times the height. So in this case it's going to be dx dy, and height is going to be the function f of x y. So double integral also will give you the volume. Okay, triple integral will give you the volume when your integrand is 1. Triple integral will give you the mass when your integrand is the function f. Double integral will give you a volume, but the integrand is going to be the height. So you are saying I want to find the volume under this function where my x values are changing from, let's say, x1 to x2, and y values are changing from y1 to y2, or as a function of x. Okay, some such thing. So you can obtain volume either from triple integral or double integral. So depending on the circumstance, depending on the problem, you would take a possible route. You cannot look at the problem. I mean, it becomes very difficult for anyone to look at the problem and say, yes, use double integral, use triple integral, or at least, let me put it this way, I cannot say it like that. Okay, I don't know, I will not be able to say it. Okay, so that's what is the introduction of triple integrals and the Fubini's theorem. I mean, it's the same thing. You can change the limits of integration. That's what they're saying. Instead of x1, x2, y1, y2, z1, z2, I'm using a, b, c, d, r, s. So that's pretty much it, the thing. Now let's go ahead and look at a problem involving triple integrals, and then go ahead evaluating this. This is going to be, let me also introduce something. Let's back up a little bit. Now triple integrals, there are like, I mean, just like in the double integral time, you have type 1, type 2, type 3, and I don't exactly remember the first type. I mean, you can just say it however you want, but the triple integral is going to be, you can write the f of x, y, z, I mean, you know, dx, dy, dz, you can write this as dA. Okay, dA is nothing but dy, dz in any order. So you can write this as dy, dz, or dv, dA. I don't know how, it's problem specific. Okay, dv, dy, or on the entire domain D. Now, another kind could be, you could have a triple integral f of x, y, z, and this time you could integrate with respect to y first and write dA. So that's going to be either, it could be dx, dz, or dv, dx. Okay, it could be either way. Then the third one could be a triple integral. You have f of x, y, z. You can have dz, and here you could have dv, dA, and dA is going to be what, dx, dy, or dy, dx. Okay, either way is fine. You could go either way. So basically, depending on the problem, whichever is convenient to me, I would go with that. Okay, now let's look at a problem and work it out for you and see. Hopefully this will help you out a lot. I need some stuff, so let me just put it that way. I need some stuff, so let's put it this way. So I need something to go under that. So this is your problem. So now you see here f is given. So that means in this problem, when we are trying to find the triple integral, you don't get really the volume. What you get is the mass. Okay, because this is the density function. The density function has no y value involved in it. This function is independent of the y value. Remember that. That's what is the key thing here. This is also an example problem in your textbook, so it's really not, I'm not doing any path breaking problem, I'm not creating a problem on my own. Okay, but this is the density function. So this is f of x, y, z is the square root of x squared plus z squared. I hope I'm on the screen. This is your density function, remember that, and the density function has no y in it. That's one key thing that you want to remember. Okay, where E is the solid tetrahedron bounded by the four planes y equals x squared plus z squared and y equals 4. Okay, that's what is your problem now. So this is not a tetrahedron. Okay, I think I copied it from the previous problem where E is not the solid tetrahedron. It is a paraboloid. Okay, is the paraboloid. It's not a tetrahedron. paraboloid. Okay, because this looks like a paraboloid for me, bounded by the paraboloid, where E is the region where E is bounded by paraboloid, that way. Okay, that way. So now how do you find it? So now it's always helpful wherever possible to draw a picture. So this is x-axis, y-axis, z-axis. So if you put if you put y is 0, it doesn't make any sense. Okay, x squared plus z squared is 0, which means x is 0, y. If you put y is 1, you get x squared plus z squared is going to be 1. So this is a circle centered at 0, 0, with 1 unit as a radius, right? So that means it's like that. It's not like this, it's like that. Okay, I hope you can see that. If y is 4, then what do you get? You get x squared plus z squared is gonna be 4. That means the circle is bigger, the radius, the center is 0, 0, radius is 2 units. If y is 9, then you get x squared plus z squared is gonna be 9, so that means the center is 0, 0, radius is 3, so you get a bigger circle. So basically what I'm trying to say is, for the different values of y, like here it is a dot, and here it's a circle, and here it's a circle, and here it's a bigger circle. So what you're gonna get is you're gonna get a paraboloid like that. That's what I'm trying to say. Okay, and I cannot go beyond. I said y equals 9, but I cannot use this. I can only go up to y equals 4. So let's say this is y equals 4. Okay, so I hope this makes sense. So this looks all messed up for me at least. So now I can come up with, like, this is my picture. Now I want to come up with an integral, so I can write this as square root of x squared plus z squared, and I can either go with dx dA, you see that, or I can go with triple integrals, square root of x squared plus z squared, dy dA, okay, or I can go with the triple integral, okay, square root of x squared plus z squared, what is that, dz dA. I explained it in the previous slide, so I'm not going to repeat it again. Now the key thing is this. Now if I want to integrate this, for all the three integrals, which one, okay, this is on a suitable domain D. Okay, let's not get into the limits of integration right away. This is on the suitable D. Okay, so now what happens is, if I want to integrate this with respect to x, it's going to be difficult for me, because I'm going to use a u substitution, and it's going to turn into something really nasty. So at least that's what I'm thinking. Now if I try using this, the same thing, I have to try some u substitution and start with integrating with respect to dz. So that's going to get turned nasty at all. But here in this one, this is, for me, this is the most convenient form. Why? Because if I start integrating x squared plus z squared, there is no y involved in it, so I can treat this as constant, and I can pull it out, and integral dy is y. So at least I get the first step in. So I want to use this formulation to find the triple integral. I'm getting the mass. Remember, it's not the volume this time. So I want to integrate square root of x squared plus z squared, okay, and I want to start with dy, and I don't know, I can go dz dx or dx dz, but let's say I go with dz dx, okay. I don't know if I'm making a right choice or not, but I'm going to go with dz dx, okay. So if you look at this, my y value is varying this way, okay, right? So that's what is my y, correct? Are you with me in that? So that means it's bounded above by the line 4 and bounded below by the paraboloid. So that's going to be x squared minus 4 minus x squared minus z squared, I think. I want to say 4 minus x squared z squared, right? So I want to say x squared plus y squared. That's what I want to say first, okay. So the next thing would be, if you look at dz, how is my z varying? My z is going to be varying from here, so that's going to be negative square root of 4 minus x squared to positive square root of 4 minus x squared. How did I get that? okay, x squared plus z squared is gonna be 4. So I mean, you know, it as z values, so that means okay, it's gonna be y, and y is bounded up by 4. So I said x squared plus z squared is gonna be 4. So I mean z squared is gonna be 4 minus x squared. So I get z is gonna be plus minus square root of 4 minus x squared. Now had I chosen to if I chose to isolate x, then that would be x equals plus minus square root of 4 minus z squared. Remember that. So now what about my x values? My x values will be varying from, okay, -2 to +2. That's what I would do. Are you with me in that? So now when you see there is no y here, so that is treated as constant. So when I -2 to 2, negative square root of 4 minus x squared to square root of 4 minus x squared, okay, and you get square root of x squared plus z squared, and you get x squared plus y squared 4, and you get dy dz dx, right? So integral of dy is a y, so that's gonna be oh god, I'm off the screen, right? So -2 to 2 negative square root of 4 minus x squared, and you get square root of 4 minus x squared, and integral of dy is a y, and the limits of integration is from x squared plus y squared to the 4, and you get dz dx, okay? So upon substituting the limits of integration, you get -2 to 2, and you get negative square root of 4 minus x squared to this positive square root of 4 minus x squared. This is going to be 4 minus x squared minus y squared, and oh, I forgot my function, right? Oh, I forgot my function. This was x squared plus z squared. So I get square root of, this is not y squared, okay, this is z squared. This is z squared, and this is also z squared. I hope you don't get confused. So this is also 4x squared minus z squared, and this is going to be x squared plus z squared, and you get what? Dz dx. Okay, I hope you are with me so far. Okay, is that clear? Okay, I'm not done, so I'm going to continue with it. So I'm going to write this integral in the next page. So I got -2 to 2 square root of negative square root of 4 minus whatever x squared, and square root of 4 minus x squared, and this is going to be 4 minus x squared minus z squared, square root of x squared plus z squared, and what do you have? You have dz dx. Now this would be one heck of an integral to integrate, but now remember we are in double integral, right? So is it a double integral over rectangular region? No. Is it double integral over a general region? Yes. But can I use double integral? But it is difficult. Can I use double integral using polar coordinates? Answer is yes. So to make it simple, I'm going to say x is going to be r cosine theta and z equals r sine theta. So upon using that, this is x squared plus z squared over circle 2, right? So this is going to be 4 minus, so I get x squared plus y squared is, x squared plus z squared is going to be r squared, and dz dx is going to be r dr d theta. So that's going to be 4 minus r squared and square root of r squared r dr d theta. I hope I'm right on that. Okay, and my limits of integration would be, for dr I'm varying between 0 to 2, and for theta I'm going full circle, so 0 to 2 pi. Okay, so that upon simplification I get 0 to 2 pi integral 0 to 2, and I get what? 4 minus r squared. This is an r, so that's going to be r squared again, dr d theta. So upon integrate, you get 0 to 2 pi and integral 0 to 2, so that gives me 4r squared minus r to the 4 dr d theta. Okay, so now you get 0 to 2 pi, 0 to 2, I get 4/3 when I'm integrating with respect to r. Now I get 4/3 r cubed minus r to the 5 over 5 where your limits of integration is from 0 to 2 in d theta. Okay, so that's going to be 0 to 2 pi, where your limits of integration is going to be 8 minus 0 minus 1/5, 32 minus 0. Okay, and that's going to be d theta. So that's going to give you integral 0 to 2 pi, so you get 32 over 3 minus 32 over 5 in a d theta. I hope I get the right answer. If I get it wrong, please fix it, okay? I have no idea if I'm getting it right or not. So anyway, this is a constant, so the whole thing can step out. 32 over 3 minus 32 over 5. And integral of d theta is going to be theta, where your limits of integration is from 0 to 2 pi, so that gives you 32 over 3 minus 32 over 5. I mean, 2 pi minus 0, so that's going to be, upon integrating whatever that is, 5 minus 332 is going to 232. 232 is going to be 64 over 15 times 2 pi, so that's going to be 128 pi over 15. Okay, I got the right answer. So that's how you perform the mass at any given point of this mass of this object is 128 over 15. If you want to know what is the physical interpretation for that, the mass is going to be the 128 pi over 15. So to summarize, what happened in this section is the following. Okay, first we introduced what is to quickly summarize, we introduced triple integral. I said if your integrand is 1, the triple integral will always give you the volume. If the integrand is f, the triple integral will give you the mass. The x is going to be the length, y is going to be the width, and z is going to be the height. But in the double integral, that also gives you the volume, but height is the integrand. Height is not the limits of integration. That's the only difference. Okay, but that's the first thing we saw. And the second thing I said was triple integrals can be viewed as 3 times. You can integrate with respect to x first, or y first, or z first. Okay, now which one are we going first depends on the problem. I cannot make a concrete statement on that. So then now I have another problem here. Okay, this is a problem. First of all, the problem was wrong. Okay, where E is the region bounded by the paraboloid. The paraboloid is that, and y equals 4 is that. The first thing is I want you to observe that the integrand is f is a paraboloid. It's not 1. So what the final answer will represent the mass, not the volume in this case. So don't think you're evaluating the volume. The second thing I wanted to tell you was to, if it is possible, sketch it. I mean, if it's not really some monster problem, sketch it. So when you sketch it, I varied the y0, 1, 4, 9 to show that it is giving me circle, and I got the paraboloid, and it is independent of the y, so I'm getting a paraboloid. Of course, I cannot go y equals 9 because the upper bound for y is 4. Okay, so now I decided I had 3 options to find the mass. I could go with respect to x first, or y first, or z first. I said I'm not going with respect to x and z because that would complicate my integration. So here there is no y, so that will be treated as constant, so I can pull it out. So I'm going to integrate with respect to y first. Okay, that's what I did. So of course I made a mistake on the limits of integration. This should have been x squared plus z squared. That should have been x squared plus z squared. This is x squared plus z squared. So now what am I doing? My limits of y, my y is varying from 0 to 4. Okay, but then if I say 0, I'm going to get this, and I'm going to get this empty space as well. But to get the limits of integration, I'm going to on the top it's bounded by y equals 4. At the bottom it is bounded by the paraboloid. So that's why I said my limits of y are from x squared plus z squared from the paraboloid to 4. And my z is going to be, it's a circle in the xz plane, so that's going to be the limits of the circle, and this is going to be the limits of the circle as well. So now there is no y, so I pulled it out, I integrated it. Upon substituting the limits, I got this and I got that. Now we are in the double integral. So is it a double integral over the rectangle? No. Is it double integral over a general region? Answer is yes. but can I integrate it? It looks like a difficult one, so I didn't want to do it. Can I use the polar coordinates? Answer was yes. It turned out to be easy, so I made a substitution. X equals r cosine theta, z equals r sine theta, and went from there. And upon integrating, I got 128 over 15. Okay, remember that. And this will give me the mass, not the volume. Okay, mind you, this will give me the mass, not the volume. I hope this helped you. That summarizes. This is one of the problems, so I hope this summarizes section 15.6, and I hope you and your families are staying safe. If you have any questions, let me know, and we'll go from there. Okay, take care. Bye bye.